Today, we're diving into a paper that explores a new way to adapt large language models for specific tasks. The paper, The Power of Scale for Parameter-Efficient Prompt Tuning, proposes a method called prompt tuning that aims to be both efficient and effective. Let's start with the basics. What is prompt tuning, and how does it differ from traditional fine-tuning?
Prompt tuning is a technique for adapting a pre-trained language model to a specific task without modifying the model's core parameters. Instead of fine-tuning all the model weights, prompt tuning introduces a small set of learnable soft prompts that are prepended to the input text. These prompts act as a conditioning mechanism, guiding the model's behavior towards the desired task. Traditional fine-tuning, on the other hand, involves adjusting all the model parameters, which can be computationally expensive and lead to overfitting.
So prompt tuning essentially adds a layer of control to the model's input. Can you elaborate on how these soft prompts are learned?
The soft prompts are learned through backpropagation, just like any other trainable parameters in a neural network. The model is trained on a labeled dataset for the specific task, and the gradients are used to update the prompt embeddings. This allows the prompts to capture the task-specific information from the training data.
That's interesting. So the model is essentially learning to understand the task through these prompts. What are the key advantages of this approach?
Prompt tuning offers several advantages. First, it's significantly more parameter efficient than traditional fine-tuning. Since only a small number of prompt parameters are learned, it requires much less storage space and computational resources. Second, it allows for the reuse of a single frozen model for multiple tasks, simply by learning different prompts for each task. This eliminates the need to store separate copies of the model for each task, making it more practical for deploying models in real-world applications.
That's a compelling argument for efficiency. But what about the effectiveness? Does prompt tuning actually achieve comparable performance to fine-tuning?
The paper demonstrates that prompt tuning can achieve performance comparable to fine-tuning, especially as the size of the language model increases. The authors show that prompt tuning becomes more competitive with scale, closing the gap with fine-tuning as the model size exceeds billions of parameters.
That's a significant finding, so larger models seem to benefit more from prompt tuning. Can you explain why this might be the case?
Larger models have a greater capacity to learn complex relationships and patterns in the data. This allows them to effectively utilize the conditioning information provided by the prompts, even with a limited number of parameters. Smaller models, on the other hand, may struggle to generalize effectively with only a few prompt parameters.
That makes sense. So the paper also explores the impact of different design choices on prompt tuning performance. Can you highlight some of the key findings?
The paper investigates several design choices, including prompt length, initialization strategy, and the pre-training objective used for the frozen model. They found that increasing the prompt length generally improves performance, but the largest model, T560L, performs well even with very short prompts. This suggests that larger models require less conditioning information to achieve good performance.
Interesting. So the size of the model seems to play a crucial role in determining the effectiveness of prompt tuning. What about the initialization strategy? Does it have a significant impact?
The initialization strategy does have an impact, especially for smaller models. The paper compares random initialization from the model's vocabulary, and initialization using class labels. We have found that initializing with class labels generally leads to better performance, especially for classification tasks. However, as the model size increases, the differences between initialization strategies become less pronounced.
That's consistent with the idea that larger models are more robust to hyperparameter choices. What about the pre-training objective? Does it matter how the frozen model is trained?
Yes, the pre-training objective has a significant impact. The paper compares models pre-trained on a span corruption objective, which is the default for T5, and models adapted to a language modeling objective. They found that models adapted to language modeling perform better with prompt tuning, suggesting that the span corruption objective may not be ideal for training frozen models that are later conditioned with prompts.
That's an important observation. So, adapting the model to a language modeling objective seems to be beneficial for prompt tuning. What are the implications of this finding?
This finding suggests that the pre-training objective plays a crucial role in determining the effectiveness of prompt tuning. It highlights the importance of choosing a pre-training objective that aligns well with the downstream tasks for which the model will be used.
That's a valuable insight. The paper also explores the robustness of prompt tuning to domain shifts. What are the key findings in this area?
The paper demonstrates that prompt tuning can improve robustness to domain shifts. They found that prompt tuning outperforms fine-tuning on several out-of-domain question-answering datasets, especially those with large domain shifts. This suggests that freezing the general-purpose language understanding parameters and restricting downstream learning to a lightweight prompt can help to avoid overfitting to a specific domain.
That's a promising result. So prompt tuning seems to be more resilient to domain shifts. Can you explain why this might be the case?
By freezing the core language model parameters, prompt tuning prevents the model from modifying its general understanding of language. This helps to preserve the model's ability to generalize to new domains. Fine-tuning, on the other hand, can lead to overfitting to the specific domain of the training data, making it less robust to domain shifts.
That's a compelling argument for the benefits of prompt tuning. The paper also explores the concept of prompt ensembling. Can you explain what this is and how it works?
Prompt ensembling is a technique for improving performance by training multiple prompts for the same task. Instead of using a single prompt, the model uses an ensemble of prompts, which can be combined using techniques like majority voting. This approach can lead to better performance and more robust predictions.
So prompt tuning offers a promising approach for adapting large language models to specific tasks. It's efficient, effective, and robust to domain shifts. Thank you for sharing your insights on this paper.